Hi class, this is Sir Alex Basco and welcome to our lesson in General Physics 1. We are talking about today work-energy theorem as well as power. So this is lesson 5.3. Lesson 5.1 we talk about work. Lesson 5.2 we talk about energy. Today we will have to combine those two together in order for us to get to know what is the relationship between work and energy, as well as what basically work-energy theorem is, as well as how we define power in physics and how we measure power in physics. So for today's lesson, the goals would be for us to be able to explain the properties and the effects of conservative forces. So we're also going to tackle a little bit more about conservative forces such as gravity. Another is for us to be able to solve problems involving work, energy, and power in different contexts, such as bungee jumping, roller coaster ride, building structures such as Great Pyramids and rice terraces. We're also going to have to solve problems involving power and energy required for human activities such as sleeping, sitting, standing, running, and walking. So a lot of things. But we're not gonna do all of these. We're just gonna do part of it. But what's important is for you guys to understand how to solve work and energy and power problems. So let's begin by understanding the relationship between work and energy theorem, or basically the work energy theorem. So basically the relationship is that when work is done on a body, remember work, um, it's force multiplied by distance. And if we applied a net force onto an object and it moves, we are applying work. So when work is done in a body, there should be a change in its motion. There should be a change in its position. It means it has to move. And the total work done on a body is basically equal to the kinetic change, the change in the kinetic energy of the system or on that body. And that relationship is what we call a work energy theorem. Okay, so the total work done in a body is equal to the change in its kinetic energy. There's a change in the kinetic energy because kinetic energy, as you have all been familiar right now, is basically the moving energy related to the movement of the object. So um, by changing the motion of a body or a system, there is a change in the kinetic energy. So when work is done on a body, it means it changes its motion. Therefore, there is a change in the kinetic energy. So that's basically how the relationship between work and energy is, no? And we have an equation for that. Basically, work is equals to the final kinetic energy of the system minus its initial kinetic energy. But how did we arrive to this kind of equation? So I'm just gonna show you quickly how we arrive on this equation. It's very simple. We've done this a lot before. So let's begin by the definition of work. In physics, we know that work is basically force multiplied by the distance. So when we apply force into an object and it moves, there is work done. This is, we know the definition of work in physics. But we also know that in physics, force is basically equal to ma. So the mass of an object multiplied by its acceleration is equals to the force exerted onto the object. And therefore, we can plug in force onto our work equation, and we would get work is equals to ma dx. So by multiplying the mass of an object to its acceleration multiplied by the distance it travels, we can actually find work. And we know this because we've defined work in physics and we've discussed about force in physics. Work is equals to force multiplied by the distance traveled by the object, and force is basically the mass of the object multiplied by its acceleration. Therefore, by substituting F to our work equation, we will get work is basically equals to the mass of the object multiplied by its acceleration and multiplied by the distance it traveled. We also know in our kinematics, you guys remember kinematics, the equation to AD is equals to V final squared minus V initial squared. We can arrange this equation and get that acceleration is basically equal to v final minus the velocity initial squared divided by 2d. So this distance here is the distance traveled to is a constant, and we have the final velocity of a moving object minus its initial velocity, both being squared. And we know that in order for us to get the acceleration of a body, we just have to get the squared of its final velocity minus the squared of its initial velocity divided by 2d. And we can also substitute this equation into our work equation right here. In the end, what we're going to get is basically work is equals to the mass of the object multiplied by Vf squared minus the V initial squared divided by 2d multiplied by dx. And this d here are basically the same. Now this is the distance travel, and what we're measuring here is basically the total distance travel if we are solving for work. Hence, we can actually cancel these two. What we're going to end in the end is basically work is equals to the mass of the object multiplied by the final velocity squared minus the initial velocity squared divided by 2. And rearranging the equation, we can remove 1/2. We will get basically, we're going to get, or we can substitute or multiply m to both v, where we're going to get m v final squared minus m v initial squared divided by 2. And we can actually rearrange this equation, and we're going to get is equals to 1/2 mv final squared minus 1/2 mv initial squared. And what you can see, remember, kinetic energy of a system, of a body, is equals to 1/2 mv squared. Virtually what we ended up having is an initial and final kinetic energy. Therefore, work is equals to 1/2 mv squared, but for final, so we're going to get kinetic energy, or the final kinetic energy of the system, minus the final kinetic or the initial kinetic energy of the system. This is how we got the equation, by basically using the definition of force and by applying the kinematics of equation. Hence, we know that in order for us to get work, what we just need is basically the final kinetic energy of the system multiplied by its initial kinetic energy. So having said that, let's try it on an example. So here we have a woman who pushes horizontally in a 2-kilogram cart with a force of 300 newtons. The cart moves horizontally at a distance of 3 meters. What is the final speed of the cart, assuming it starts from rest? So let's begin by writing our given. So given for our problem, we begin with a woman who is pushing this cart with a mass of 2 kilograms. So the mass of the cart is 2 kilograms. And then she is pushing with a total force of 300 newtons. And we know the distance traveled by the cart is basically 3 meters. What is the final speed of the cart, assuming it starts from rest? And since it's from rest, we know that the initial velocity of the car, since it starts from rest, should be 0. And what the question is asking us is the final speed of the cart. And the formula that we have to use is the formula we just derived earlier. We know that work is equals to the kinetic energy, final kinetic energy, minus the initial kinetic energy of the system. In this case, the system is the cart and the woman. and the woman is exerting a force on the cart, so we can isolate the cart as our system. What we have to do first, let's do the solution. Since we know this is our equation, and we know what we're looking for is VF. So what we're looking for, the missing part is in the kinetic energy. So what we have to do first is solve for work. And we know that work is equals to force multiplied by dx. And we know that the woman is exerting a 300 newtons of force onto the push cart, and it traveled at a distance of 3 meters. Hence, 300 multiplied by 3 is basically 900 newtons, or 900 newton meter. 900 newton meter, or basically 900 joules. That's the unit for work. Next, what we're going to do is we're going to have, after solving for work, we're going to use this to equate our equation here now. So we have, let's use Newton meter as our unit. So we have 900 Newton meter is equals to KE, or let's write it here. Solve for the final velocity. What we're going to do is we're going to use our found work, and we're going to use that to equate using our formula. So we're going to have 900 Newton meter is equals to the kinetic energy final minus the kinetic energy initial. But we know that the equation for kinetic energy is equals to what? 1 half mv squared. So let's just substitute that. We're going to get 900 Newton meter is equals to 1 half mv final squared minus 1 half mv initial squared. And we know that our initial velocity is 0. So plugging in the numbers, we're going to get 900 Newton meters is equals to 1 half. The mass of the object is 2 kilogram multiplied by final velocity squared minus 1 half multiplied by 2 kilogram multiplied by 0 squared. And we know this should be 0 because anything multiplied by 0 is 0. So we're going to end up having 900 Newton meters is equals to 1 half kg VF squared. And then what we're going to do is we're going to have, not kg, this should be 2 kg. What we're going to do is basically we can just cancel this. No, we can just cancel that, and what we're going to get is basically VF is equals to the square root of 900 Newton meter per kg, and would actually give us a final velocity of 30 meters per second. Square root of 900 is 33. 30 times 30 is 900. So it's kind of like easy. Even without calculator, you should be able to use this. Okay, so that's basically it. That's how we solve for the final velocity in our equation. So we derive the final velocity from our KE. This is kinetic energy, not just K. Okay, so I hope that's clear. So that's basically the relationship between work and energy, more specifically kinetic energy. Now let's go on discussing conservative forces. So we've discussed a little bit about conservative and non-conservative forces. We know that for conservative forces, another thing that you have to remember is that it can be represented by potential energy. The reason it can be presented, sorry about the noise if you guys can hear that, apologize for that, but yeah, Conservative force, we know in conservative force, it can be represented by potential energy. The reason for that, because work done in conservative forces is independent of the path. It only considers the final and the initial position of the system, or in this case, of the object. So again, remember for conservative force, we do not care on how we arrive, no? We do not care about the path. Well, what we only care about is the initial position and the final position. Example of this is gravitational, elastic, and electric forces. As opposed to non-conservative forces, for non-conservative forces, we cannot represent it by potential energy. The reason for that is because the work done depends on the path. An example of this is friction and drag forces. Drag forces is basically like air resistance or the drag on the water as the both travels through the water. Those drag forces, they are dependent on the path. The reason for that, if you think about it, no, gravitation changes depending on the height of the object. Yeah, we've discussed this a long time ago, pero lagi natin ginagamit yung gravitational force is basically always 9.8. That is actually just average. In reality, the gravitational force changes depending on the height of the object, and it depending on basically the height. So no, if you think about the height, that's more on the position. No, the higher you have, no, I think the lesser the gravitational force is, and the closer you are to the ground, I think it was the lesser or probably the opposite. But yeah, what I'm trying to say is gravitational force, it is more on the position of the object. The same thing with elastic. We talk about elastic when we talk about spring. No, we do not care how we stretch the string. What we care about is the initial length of the string and the final length of the string as we stretch it as stretch it out. And the conservative force, or we can measure the force or the work done, yeah, or the kinetic force or the energy of the system, depending on the length of the string, basically again the initial and the final position. That's why conservative forces can be represented by potential energy. We only care about the initial and final positions. As opposed to non-conservative forces, we cannot represent it with potential energy because we have to um, consider all the path taken. For example, in friction, if you want to measure the friction, this is basically the contact between the object and the surface. And as the surface travel, there's gonna always be friction everywhere, no? And you can calculate the friction force by considering all the friction exerted by the surface onto the object. So meaning the more you drag, for example, a box onto the floor, uh, as you keep pushing it, friction will always be there. So it dependent on the path, no? The same thing with drag. Drag force, example, air resistance. As a ball drop from, kapag, let's imagine, umakyat kayo sa rooftop ng bahay nyo and then hinulog nyo yung bola. And that ball will experience a drag force and air resistance as it goes down, no? And that air resistance is throughout all the path as it goes down. It's not only in the initial and the final position na merong drag force or merong air resistance. Air resistance is everywhere as it drops down. That's why it depends on the path. It's not only dependent on the initial and the final positions. That's the difference between conservative force and non-conservative force. However, one thing that is interesting is that conservation of energy or energy can actually be conserved. We know that in first law of thermodynamics that energy cannot be created nor destroyed. It can only be transformed. Example, we have heat energy, we have chemical energy. We can use the heat energy to make it into mechanical energy, no? Or we can use chemical energy and transform it to heat energy, but we cannot create nor destroy that energy. We can only transform it. That is the first law of thermodynamics, and that is a well-known law. But what I'm trying to say that is interesting is that even if we transform the energy, the total energy in the universe or in the system is conserved. What do we mean by that is, for example, we have chemical energy and heat energy. If we transfer or transform chemical energy into heat energy, the total energy pa rin ng buo is basically equal. So how am I going to explain this? So let's see. Okay, so for example, you have chemical energy and then you have heat energy, you know? So let's say you started 100 on chemical energy and then you want to transform that chemical energy into heat energy. What happens is that, so this is the start, no? And then at the end of the reaction, maybe what you're gonna have is chemical energy, probably gonna have 20 because it transforms 80 into heat energy. Pero yung total energy of the system at the end of the reaction, let's say this is your end of the reaction, this is your beginning reaction. As you can see, yung total energy pa rin niya is equals the same, no? Equal pa rin sila because we cannot create nor destroy energy. It is conserved. If we change or if we use chemical energy and transform it to heat energy, um, the amount of energy transform into heat energy, kapag pinag-add mo sila in the end, it should still be equal. I'm not sure if I explaining this properly, pero rest assured, if you transformed it, the energy is conserved. Hindi siya bigla-bigla na lang mawawala, no? Yes, it becomes entropy, but that just means that that energy cannot do work anymore. Pero it's still there, it's somewhere there. And if you take that escape energy by entropy and take it into consideration and add everything out, the energy that is in the system overall should still be equal. Here's like an example, no? But let's consider this as an equation for now. So the mechanical energy in a system is conserved. So what do we mean by that is potential energy plus kinetic energy, and this is still going to be equal. What do we mean by that is, let's take this an example. So you have a card, beginning card here, wherein the kinetic and there's less kinetic energy and there's more potential energy. But we know that if the object starts to move faster, and we know that when things fall down or when things go down, they move much faster. And the faster they are, the higher the kinetic energy. As you can see here, it goes down, it moves faster. So tumaas yung kinetic energy niya, pero and then yung potential energy niya bumaba. Pero if you still look at this, in total energy ng dalawa, kapag pinagsama mo, it's still gonna be equal. Kasi once na tumatas yung kinetic energy, yung potential energy nawawala. Pero take into consideration, kapag nag-start na siyang tumaas, bumabagal siya. And we know when things go up, bumabagal sila. And slower they are, the lesser the kinetic energy is. And since tumataas sila, there is a change in height, no? And pinag-usapan natin kanina, potential energy is affected by height because gravitational energy, no? That's PE. And as it increases, it goes up, the potential energy increases, but the kinetic energy decreases. But the overall energy between the two would still be the same. So let's say first this starts at 60 and 40, now this becomes 100, but this is 0. Pero as it goes up, this starts to increase, but then this starts to decrease. Pero again, kapag pinagsama mo pa rin yung dalawang ito, it's still gonna be equal. Yung energy niya na nandito siya, yung energy niya na nandito siya, yung total energy, okay? Yung total energy niya na nandito siya, yung total energy niya na nandito siya, or anywhere in any point of this slope here, it's still gonna be the same kasi hindi nawawala yung energy. We just transform it, we just transform. In this case, we transform potential energy here into kinetic energy as it goes down, and then we transform kinetic energy into potential energy as it goes up. No? Parang nagpapalitan sila, nagbibigayan lang sila, pero hindi na wawala yung energy. That's what we say that it is conserved. The total energy between the two will always be constant, and that is the total energy um, in the system. And we can actually measure this total energy. No? Let's have this as an example. So a student from a physics class visited an amusement park to test their understanding of mechanical energy. They ride a roller coaster that starts from rest at point A. So we have a roller coaster that starts from A and it moves without friction. Is necessary because otherwise we have to consider friction. Determine its speed at point B, point C, and point D. What constant deceleration must be, not ebb, must be applied to point D to bring the car to stop at point E. So there's a lot of things going on. So let's go on to the here you go the whiteboard and let's try this problem. Okay, so students from a physics class visits an amusement park, no? Because we try to understand the conservation of the mechanical energy. They ride a roller coaster that starts at A, and at A, at A, the roller coaster is 20 meters above the ground. And then we want to identify what would be the speed of the roller coaster as it reaches B, as it reaches C, and as it reaches D. And then how much deceleration um, the roller coaster needs in order for us to stop it at point E. So how are we going to solve this? Okay, so this is basically yung given na, no? So let's just write this as our given already. And then, let's write ano ba yung tinatanong sa atin. So basically, it's asking what would be the velocity at B, what would be the velocity at C, and what would be the velocity at D. It's also asking how much acceleration do I need, or in this case, deceleration. Deceleration is just basically type of acceleration, but instead of increasing the speed, we are decreasing the speed. So basically, kind of like you can imagine if it is a negative acceleration, negative that in a sense that it is opposite the direction of the movement. Okay, so how much acceleration do I need so that it stops at letter E? So how are we going to solve this? So let's think of our formula. So the formula that we know is basically the formula that I showed you earlier. We know that the total mechanical energy is conserved. So the potential energy of the system plus its kinetic energy should be equal to the total energy, and that no matter where the point is, kapag tumaas ito, bababa ito. Kapag tumaas ito, bababa ito. And it will always be constant. And we know that the potential energy of the system, in this case, the potential energy of the, in this case, the gravity, since we're looking at the roller coaster, should be mgh, and the kinetic energy should be 1/2 mv squared. Okay, so how are we going to solve this? So, one thing na hindi binigay sa atin dito is yung M, yung mass ng roller coaster. The same also, that mass should include yung mass ng mga tao na nandun sa roller coaster. So what we're gonna do is we're gonna use X. We're gonna use letter X to denote the mass of the object. Okay, so just remember that we're going to use letter X to talk about the mass of the object. So let's start with the solution. So what we're gonna do is we're gonna start with point A. At point A, we're gonna do is we're gonna measure the potential energy of the uh, roller coaster at point A. And what we're gonna do is we're gonna measure first. Yeah, we're gonna measure the potential energy. We know that potential energy is basically equal to mgh. We're gonna use x to talk about the mass of the roller coaster and all the people riding in it, multiplied by g, which is 9.8 meters per second squared, multiplied by the height that the roller coaster is in, which is equals to 20 meters. And we know that the potential energy uh, of the roller coaster in point A is actually equal to 9.8 times 20, that's 196. Yeah, I'll just write 196. Multiplied by x, so that's 196. Um, yeah, 196 x, and we're gonna use j because x here, this is kilogram, it's still kilogram per second squared. That is basically joules, so potential energy is in joules. And then we're gonna solve for kinetic energy. We know that um, at A it starts at rest. It starts from rest at point A. Since at rest, let's just write it here, meaning it's not moving. If it is not moving, therefore the kinetic energy is basically zero. So in the end, we know at point A, the total mechanical energy at point A is PE plus KE. So that's basically EM is equals to 196x J plus 0J. So EM is equals to 196x joules. Okay, so I hope that is at this point it's clear. Next, what we're gonna do then is consider point B. At point B, what is happening? We're just basically gonna do the same thing. We have to measure the entire mechanical system at point B. So we're going to begin measuring the potential energy at point B. We know mgh as well, no? And we're still gonna end up with x multiplied by 9.8 meters per second squared, multiplied by the height at point B. It's just 5 meters, and therefore the potential energy at point B is actually equal to 49 x joules. And the kinetic energy at point B, because dito at rest siya, pero roller coaster will continue moving, so it's already moving at point B. Therefore, there's a kinetic energy at point E, and we know the kinetic energy is equals to 1/2 mv squared. So are we going to measure point B? We don't have to have the mass, and what we're looking for velocity. So what we're gonna do is EM is equals to PE plus KE at point B, and we know that EM here is basically equal to 49 x J plus some KE. Tama? Kasi at point B, remember yung moving picture kanina, when you start to go down, you move faster. Therefore, yung potential energy mo nung hindi ka umaandar, yung potential energy mo nung at rest ka, the potential energy caused by the difference in the height, no? when you starts to move, nababawasan yung potential energy mo as it converts to the kinetic energy. So, kung papansin nyo sa point A, hindi ka gumagalaw, meron kang potential energy na 196 J joules, 96x joules. That x is the mass, again, of the roller coaster. Pero once you start to move, mababawasan yung potential energy mo, it converts to kinetic energy. So, but again, the interesting thing is yung total energy mo dito and yung total energy mo sa B should be equal because it's conserved, no? Therefore, what we're going to do is we can equate these two because they're both equal to EM. So we're going to do the potential energy at A should be the potential, or the total energy at A should be equal to total energy at B. And therefore, 196x joule should be equal to 49x joules plus Ke. Tama? And then we can move K. We're going to have 196x joule minus 49x joules is equals to 1 half mv squared. In this case, our m is still x. Yeah, because m is, we're going to use m to denote x, no? Okay, well, we're going to do that. We're just going to subtract this, and that's gonna give us basically 46 or 96 minus 49. That is basically 147 x joules is equals to 1 half x v squared multiplied both sides by 2. This cancels 2, and then divide both sides by x. Let's just start to multiply, and then divide both sides by x to cancel the x. So na-cancel yung x, and that would gives us basically v. In this case, this is the velocity at b, is equals to the square root of 2 multiplied by 147 joules, and that actually gives us 17.1 meters per second. So that's how you solve now for, or so we were able to solve for the speed of the object as it goes to B. No? Next, how are we going to solve for C at point C? It's the same thing, no? You just have to follow the same thing. So find the potential energy, which is mgh, and we know that would be x multiplied by 9.8 multiplied by 16 meters. And that will give you, let me just look at my notes, 9.8 times 16, that's basically 156.8x, or basically 157 x joules for your PE. Again, for kinetic energy, it's some kinetic energy, so the total system at point C is equals to 157 xj plus ke. And again, the system is conserved, so A should be equal to C. There's the total energy at A should still be equal to the total energy of C. And kung papansin nyo, biglang tumaas again yung PE mo, yung potential energy mo, kasi tumaas din yung height mo. No? And remember, that's the moving picture natin kanina. As you go up, you slow down. And since you slow down, bababa yung kinetic energy pero tataas yung potential energy. So pagdating mo sa C, you're still moving pero mas mataas yung potential energy kasi bumagal ka sa C compared dun sa speed mo kay B. So you should expect that the speed at C should be somewhere lower than, or yeah, your speed at C should be lower than your speed at B. So what we're gonna get, the same thing, we're gonna have 196 x joules is equals to 157 joules plus KE. So 196 x joules minus 157 x is equals to KE, or basically 1/2 mv or xv squared. And then just, just minus this, divide both sides by x. You can cancel the x, and then multiply both sides by 2 to cancel that. Multiply this by 2. In the end, you're gonna have the velocity at c should be the square root of 2 multiplied by 196 x joules minus 157 x joules. Just use calculator and you would get the velocity at c should be actually equal to 8.83 meters per second. And for d, just do the same thing and you will get that the velocity at d is actually equal to 14.0 meters per second. I'm not going to show how to solve d because it's basically the same thing, no? So I hope that is clear. The point of this is to show you that the energy is conserved. Your total energy at A should still be the total energy no matter where the point is, because the energy is conserved. Dito lang wala kang kinetic energy sa point A kasi you're at rest. No, you're at rest at point A, so you don't have any kinetic energy. You have zero kinetic energy. Everything is in potential energy. But once you go down, you start to move. And especially as you go down, you're being pulled by the gravitational force of your weight, therefore increasing your kinetic energy and lowering your potential energy. You lower your potential energy kasi you're going down. And magiging zero lang yung potential energy mo kapag nasa ground ka. But since there's still height, you still have potential energy left. But most of it is in the kinetic energy now. That's why you have very low kinetic or potential energy because most of it is in the kinetic energy in form of speed. That's why medyo mataas din yung speed compared sa C kasi pagdating sa C, bumagal ka. Therefore, bababa yung kinetic energy, babalik ulit siya dun sa potential energy. As you can see, hindi siya equal dun sa A kasi mas mababa yung height mo sa C compared sa A. Pero once you go to 20 sa C, kapag nasa 20 ka ulit, ang mangyayari mo, you just basically went back to your original height. So mapupunta ulit lahat siya dun sa potential energy. But in this case, dahil mas mababa yung C, no, 16 meters lang compared sa 20 meters, mas mababa yung potential energy mo kasi you have some the kinetic energy. Okay? So, and then, since again, conserve yung energy, yung total energy mo sa A should still be your total energy at C kasi constant lang siya, no? And therefore, you can solve for the speed using the same ginawa natin kay B. And to solve for the velocity at D, you just have to do the same thing. And it happens to be 14.0 meters per second. And lastly, in order for us to find, so this is the fourth. And then fifth, in order for us to find the deceleration from points D to E, you just have to use the kinematics of equation. And the kinetics of equation, we know that 2AD is equals to V initial squared minus V final, or V final squared minus V initial squared. And we know since we want to stop at E, we want to have our E final as 0. No? So meaning this is basically 0 because we want to stop this. So in the end, what we're going to have is basically negative V initial squared divided by 2V. And yung V initial natin is just basically your speed at VD. So you're going to have A is equals to negative 14.0 meters per second squared divided by 2 multiplied. Distance between D and E is 15 meters. And therefore, your deceleration to stop you should be negative 6.3 or 6.53 meters per second squared. This is the deceleration you need if you want to stop the roller coaster moving at 14 meters per second at D to 0 final velocity at E. Okay, so I hope that is clear. That's how we conserve mechanical energy. If you guys have any question, please do not hesitate to message me. And let's move on to our last part of our discussion, which is power. It's quite easy. Power is basically, or in physics now, when we talk about power in physics, it's basically a measurement of how fast the work is done. So we are just adding an element of time. So how fast? So we are adding an element of time. We know that work is equals to FD. No? Therefore, how much work you done over a period of time is basically power. So power is equals to work divided by time because it's the amount of work over a period of time. And we know that that's basically power is equals to work divided by time, or FT divided by dt. But what's interesting here is that d over t, you guys remember this, is basically distance over time is basically velocity. So meaning power is basically force multiplied by velocity. So the force, the the product of force and velocity is power. And the units we use for that is what we call watts. And we use capital W again to denote the units. So let's try this as an example. A boy whose mass is 45 kilogram runs up with 25 steps, each step 30 centimeter high in 50 seconds. Find the power in watts expended by the boy. So how are we going to do this? Let's write our given. We know the mass of the boy to be 45 kilograms. And he's traveling, is running up. Now he's going up 25 steps, and each step is 30 centimeters in height, or 30 centimeters high. No, what we just need is measure the height, and we know that the height is 25 steps multiplied by 30 centimeter per steps. Cancel the steps, and 25 multiplied by 30, you would know that it's basically 750 centimeters, or that is equals to 7.5 meters. So the boy went upwards of 7.5 meters. And the time it took for the boy to move or to work is equals to 50 seconds. And then, ang tinatanong is basically the power. The formula that you have to use is basically P is equals to, it's basically FD That's basically work divided by time. Solution. So you have power, work divided by time. We know that work is, in this case, since you are going up and down, it's not horizontal, it's vertical. No, the force that is being exerted here is basically mgh, no? So the force over time. And the force being exerted in this case, since the boy is going up a stairs, is mg, is weight, no? And that gives us mg, and the distance is basically the height over time. Therefore, the power that is being used is 45 kilogram multiplied, this is the mass of the boy, multiplied by the pull of gravity, which is 9.8 meters per second squared, multiplied by 7.5 meters divided by 50 seconds. And the total power used is equal to 66.2 watts. So that's how you solve power. So you just have to identify the force and the distance, or the velocity. So if they gave you the speed of how fast the boy is moving and you know the force, you can solve for power. So that's quite simple what power is. It's just we're adding the element of time in our work. No? So I hope it's clear. That's how you solve for power. And if you guys have any questions, do not hesitate to message me. Thank you so much and have a great day.